Hello, class. I am re-recording this lecture that we had on last Thursday, which would have been, January 22nd. Mostly because of the technical issues that I had with my Apple Pencil in the middle of class, so you'll remember I had to go up to the whiteboard. So I'm just going to re-record to make it a clean recording of this lecture. So last week we talked about, or rather earlier in last week, we talked about normal and tangential coordinates. In this class, we're going to talk about radial and transverse coordinates. So both coordinate systems are a little bit more complicated than our regular Cartesian coordinates. So we talked about how Cartesian coordinates, we place them in the world, and then they never move thereafter. No matter what happens to the particle, it can be flying around through space out here, that Cartesian coordinate system doesn't go anywhere. It stays right where it's at. That is different than our normal and tangential coordinate systems and our radial and transverse coordinates, because we know that these coordinate systems are essentially attached to the particle. And so as the particle moves through space, so do these coordinate systems. And the fact that these coordinate systems are moving and changing in time is what makes our definitions of position, velocity, and acceleration a little bit grosser than they would be for Cartesian. Okay, so all that said, a particle moving along a curved path may be conveniently described using cylindrical or radial transverse coordinates instead of Cartesian. And so those are just two different names used for the same coordinate system. I will sometimes call them the r theta system, and we'll use theta whenever we're denoting the transverse direction. So it's the radial and transverse coordinate system. So let's draw a quick picture of what this looks like. Now, the interesting thing about the RT coordinate system, or the r theta, is that you actually have to define two kind of extra quantities in order to fully define this coordinate system. So the very first thing that we have to define is an origin. So we have to say, okay, here is the origin of my coordinate system. And I like to just put my Cartesian coordinate system there, just kind of out of habit, but just to also kind of compare between the Cartesian system and the radial and transverse that we're about to draw. Now, similarly to normal and tangential, to draw the rest of it, we really need to know what the path of the particle looks like. So this green thing will be the path. And we'll place my particle on the path maybe somewhere right here. Okay. Now, the next thing that I need to draw is the radial direction. And the radial direction is defined as pointing away from the origin. And so we draw a line that connects the origin to my particle, like this, and then the radial direction is like an extension of that line, right here. That's my radial direction. And we will often refer to this quantity r as like the distance from the origin, and that's actually how we'll define the position of this particle, as being some amount in the radial direction. Okay, now the next thing we need to define is an angle. We need to set what is a positive angle, and so we need to show how theta is going to be measured. And so what is kind of most traditional is to measure theta from the positive x direction to your radial direction. And that will be the direction of positive theta. So notice that I drew an arrow with only one arrowhead, showing that theta grows as this radial arm sweeps in this direction. Okay, so theta gets bigger as we go counterclockwise. Okay, and now we know that for any coordinate system, our coordinate directions are perpendicular to each other. And so for our transverse direction, we really only have two options. We can either point up and to the left this way or down and to the right that way. And the way to memorize the correct direction is that the u hat theta direction points in the direction of increasing theta. So what that means is that if I were to hold my radial direction constant and I take this particle and I start spinning or increasing theta, we'll see that the particle moves up and to the left as we increase theta. It does not move down and to the right as we increase theta, okay? So the correct direction for positive u hat theta is up and to the left. I'm going to make this bolder here and this bolder here. And I'm going to redraw this coordinate system quite a few times in the rest of these notes, so hopefully by the end of the notes you'll get a hang of which direction u hat theta goes. Okay, let's put in some words to describe how we drew this coordinate system. So we said u hat r, or the unit vector in the radial direction, is in the direction of increasing r when theta is held constant or fixed. And just as a reminder, we define this r as a magnitude or distance from the origin. Okay? All right, let's see now. U hat theta then is in the direction of increasing theta when r is held constant. All right. So I really try to visualize what's happening here in terms of these definitions. I try to think about holding, a fixed distance from the origin and then spinning that stick in the direction of increasing theta to try to figure out what direction u hat theta points. It's a very visual piece of memorization. Okay, so now let's relate our position, velocity, and acceleration to this coordinate system. And as I did last time for our NT coordinates, I'm going to remind ourselves of these, of how we define the Cartesian system and on the left-hand side, and I'll show the RT definitions on the right-hand side. So the Cartesian coordinate system also required us to set an origin, right? We had to place that XY coordinate system in our space. And then the position of the particle was defined relative to wherever we put that origin. So that's kind of similar. So again, I'm going to go through the song and dance of drawing this coordinate system, and then we'll show how we define the position vector. So I'm going to set this origin O. And then I like to go ahead and draw my radial direction, which is just the line that connects the origin to the particle and then extending out past that. So this is u hat r. And then I need to define my theta. So I like to define theta as being the angle from the right-handed side horizontal counterclockwise to my radial arm. But as we talked about in class, this is a personal choice. You could technically decide to place theta like this in the opposite direction, okay? You can define it however you want, but you have to be consistent. Okay, so if we were to define theta in this direction, it would change which direction we call our positive u hat theta. So if I'm going to be 90 degrees from u hat r, and I'm going to point in the direction of increasing theta, and theta increases in this direction, then that means it's this direction that has to have u hat theta. Okay, so that's a personal choice. Like I said, I just default, I like to go in the other direction. It's just a little bit more common to measure from the kind of positive x direction, if you will. So I like to go this way, that's theta, which makes up and to the left the u hat theta direction. Okay, and of course these are 90 degrees to one another. Okay, and we said that the distance from the origin is this scalar r, and we say that the position vector r is equal to just r, the magnitude or the distance along the u hat r direction. Okay, so position in RT coordinates is quite simple. All right, let's scoot on down to velocity. And I'll do the same thing. I'm going to redraw it just to give us more repetitions. So I'm going to set an origin. I then like to immediately define my radial direction. I draw a line from the origin out to the particle and extend out in that same direction as my u hat r. Then I define my theta. I like to go from the positive x direction to my radial arm, theta, which means that my u hat theta direction points this way, in the direction of increasing theta. So if I were to increase theta and push this radial arm here, I push that around the circle as theta increases. That means this point is going to go up and to the left. So that's my u hat theta direction, which I failed to label. So let me label that real quick. U hat theta. Okay. Now, we've talked before about how it is absolutely valid that for all of these coordinate systems, velocity is going to be equal to basically the time derivative of our r vector. Okay. However, what gets gross is the fact that we defined our r vector up here in terms of a unit vector that in and of itself, that unit vector changes through time. So when I say that velocity is equal to the time derivative of r u hat r, this is a quantity that depends on time, and this is also a quantity that depends on time. So to do this derivative correctly, I would need to use product rule. I would need to say that velocity is equal to the first times the derivative of the second, plus the second times the derivative of the first. And what gets gross is trying to figure out what the heck is the time derivative of this unit vector. And I said it is possible to prove that u hat dot r is equal to theta dot u hat theta, but that I don't think that you really need to understand that proof for this class. So we're not going to worry too much about really understanding the derivation of velocity and acceleration in RT coordinates. All I need for you to know how to do is to manipulate the equation that I'm about to give you, or the equations I'm about to give you. Okay, so actually, if you want to believe me that this is true, you'll see in just a moment that velocity is equal to r theta dot u hat theta plus r dot u hat r. Okay, so just plugging in this for this derivative of u hat r. Okay, so I'm going to erase to make this cleaner. And I'm just going to write out what you need to know how to manipulate. You don't need to know how to prove this. And in fact, this expression, V equals R theta dot U hat theta plus R dot U hat R, that will be given to you in your equation sheet. And I believe in class I reminded you that my recommendation is for you to go ahead and print out those equation sheets that are on Canvas and have those with you every time you do your homework so that you can practice interpreting the equation sheet, knowing where the important equations are, so that you're just super well practiced with using that equation sheet by the time you need to use it on an exam. So now is a really great time to start doing that. Okay, let's do the same thing for acceleration. So again, got to set my origin. Not sure why I don't have a path already drawn here. Sorry about that. We'll do a path, put my particle on that path. And I like to draw my radial direction from the origin out to the particle and then pointing in the same direction out from the origin. And then I like to set my theta. I'm going to say that theta pushes this radial arm up and to the left or counterclockwise, which means that U hat theta points this way. And these are 90 degrees to one another. Okay, the actual position, velocity, and acceleration vectors, we talked about this in class too. The actual position, velocity, and acceleration vectors, they do not change based on the coordinate system that you choose. So this vector on the left for Cartesian acceleration, exact same acceleration here. Velocity here, oh, I should have copied this one too. This velocity vector, copy, paste, exact same velocity vector. Oh, so this, I should have drawn this a little bit differently because what I don't want you to do is see the way that it's drawn here where it looks like the velocity vector is perfectly aligned with the radial direction. That is not always the case, and in fact, it is mostly not the case. It's just the way that I have it drawn here. It just happens to be the case at this moment. So I'm going to erase that for now. But all this to say that this R, V, and A vector, those are properties of the way the particle is moving around the path. And they don't change at all depending on which coordinate system you choose. It's just a different way of expressing the same vector. Alrighty, let's see. What is our acceleration? Again, if you wanted to rederive this, you could say, and it would be perfectly valid to say, that acceleration is equal to dv dt, but you would need to use v expressed in u hat r and u hat theta coordinates, so this would be d dt of r theta dot u hat theta plus r dot u hat r. And again, you're going to have now 3 things that depend on time and 2 things that depend on time. So you're going to end up needing to do product rule kind of all over the place in this. And this derivation gets really, really gross really quickly. And I don't think it's important that you know that derivation for this class. So I'm going to skip the derivation and simply tell you that acceleration, do it in red because it's important, acceleration as a function of time. This could also be a function of time. This could also be the function of time. Acceleration as a function of time is, r double dot minus r theta dot squared in the u hat r direction plus r theta double dot plus 2 r dot theta dot in the u hat theta direction. Okay, so we will need to know how to manipulate this equation, and this equation, but you do not need to know how to derive them, so how to prove them. Okay, a couple of things to note. It's important to see that the above equations depend on the following quantities. We have r dot, r double dot. Sometimes we'll need to mess around with theta, although I don't think theta on its own actually shows up in any of these equations. But theta dot does, and so does theta double dot. And when I say dot, it's important to remember that the dot notation refers to a time derivative or a derivative with respect to time. That is to say, r dot is equal to dr dt specifically. So it is not the same. R dot is not equal to, for instance, dr d theta. Okay, so this denominator matters in this derivative. And let me maybe give you a solidifying example of what I mean here. So in a lot of the problems that we'll do for r theta coordinates, we might be given r equal to a function of theta. So maybe we're given something like r equals 2 theta plus theta squared, perhaps. The question will be that we need to, in order to fill out our position, velocity, and acceleration equations, we need to find those r dots. So how can we find r dot? We can't take dr d theta and call that r dot. Well, what happens is usually these problems will not just give us r as a function of theta, they will then give us also that theta is a function maybe of time. So maybe 2t squared plus 4t plus 2 perhaps. So we need to do the chain rule to find r theta. So if we need to, to find r dot. So if we need to find dr dt, this is equal to dr d theta times d theta dt. Okay, so dr d theta we can find directly from this expression, and d theta dt we can find directly from this expression. So we just need to multiply the two together to find r dot. Okay, and note that this is theta dot. So I like to think of this as almost like a unit conversion because I think about the d thetas canceling and I'm left with dr dt. So let's maybe finish up this example. So if I need r dot, let's find dr d theta. Dr d theta would be equal to 2 plus 2 theta. And then d theta dt would be equal to 4t plus 4. Okay, so for this example, dr dt or r dot is equal to dr d theta times d theta dt. Okay. And if you'll notice that we have thetas and t's, which is a little bit awkward. So what you could do is then substitute in theta is equal to 2t squared plus 4t plus 2, and then this whole expression will be in terms of t. Okay, so just an example. Okay, let's move on to our first working example. Whoop, we already did that. So our first in-class example, we said, all right, we want to find the magnitude of acceleration when t equals 2 seconds for this particle that is moving around a perfectly circular path. So we're going to pretend that Dr. Higgins can draw a perfect circle, and that's this green path. And this perfect circle we see has a radius of 300 millimeters. And we're given that theta dot is equal to 2t squared radians per second. Okay, so I'm given in this problem something about a radius and a theta dot. Now, neither of those variables show up in my normal and tangential coordinate system, but both of those variables show up in my r theta coordinate system. So I'm going to take a guess here that my r theta coordinate system is a good choice for this problem. And then I'm going to write out my expression for acceleration in terms of that coordinate system, because acceleration is what it's asking me for. So I'm going to go ahead and write down, okay, if we're going to find acceleration, I need to be able to fill out this expression here. Which means that I need to go find r, I need to find theta double dot, I need to find r dot, theta dot, r double dot. I think I already said r and theta dot. So we need to go find each of those quantities. So I'm going to write myself a list. We need to know, or we need to find r, and I'm even going to say r when t equals 2 seconds. R dot when t equals 2 seconds, and r double dot when t equals 2 seconds. We'll also need to know theta dot when t equals 2 seconds, and theta double dot when t equals 2 seconds. Now, some of these quantities will be 0. Okay, now how do I know that? Well, I like to start at the top and work down. So if we start with the radius, I know that I'm moving about a perfect circle whose radius is 300 millimeters. So no matter where I'm at on that circle, this r value is going to be 300 millimeters. And that is never going to change because it's a perfect circle. The distance from the origin here will never change no matter where I'm at on that circle. And so the change in r with respect to time is 0. There's no change with respect to time. And if r dot is 0, r double dot is also 0. And that's because the radius, radius of circular path doesn't change. Okay, now theta dot is given to me in the problem as 2t squared, so I can go ahead and plug in t equals 2, and I should get 2 times 4, which is 8 radians per second. But then I need to also find theta double dot. So theta double dot will be just taking another time derivative of theta dot. So if theta dot is 2t squared and I take another time derivative of this, that means theta double dot should be 4t. And if I plug in t equals to 2 seconds, that means theta double dot at 2 seconds is equal to 8. 8 radians per second squared. And now I have all the quantities that I need to find my vector A. So I can say acceleration is equal to 300 millimeters times theta double dot, which is 8, plus 2 times r dot, which is 0, so that whole second term becomes 0. This is u hat theta, plus r double dot, which is 0, minus r, which is 300 millimeters, theta dot, which is 8 squared, all in the u hat r direction. We should get that acceleration is equal to 2,400 u hat theta minus 19,200 u hat r, and this will be millimeters per second squared. But the problem doesn't ask me for just acceleration. The problem asks me for the magnitude of acceleration. So the magnitude of acceleration is the square root of each component squared. So I should get 19,349 millimeters per second squared. And that's our first problem. All right, example 2. Example 2 is going to be a little bit harder. There's some little tricks that we have to work through to get this one. So let's first start out by understanding this picture, because I don't know that I drew it very well. This green kind of bean looking thing, this green groove, is like a slot. It's a slot that defines the path of this little blue ball. So this little blue ball is being pushed along this slot by this pivoting arm. And this ball can kind of move freely up and down this arm. So this arm is kind of like hollow, like this. And the ball is inside of this hollow part. So as the radial arm moves left and right, it pushes the ball along this grooved path. Okay, so the groove defines the path, and we're actually given r as a function of theta to define that path. Okay, we're also given theta dot, and then we're given some initial conditions that says when theta is equal to pi over 3, this is time equal to 0, and velocity at that point is also equal to 0. Okay, so those are just initial conditions. They're giving you one snapshot in time. They're saying when time equals 0, the angle is at pi over 3 and the velocity is 0. And we're asked to find velocity and acceleration not at time equals to 0, but at time equals to 1 second. So let's start out with our velocity. Again, I'm going to say if I have this origin O, this radial arm here certainly seems to be defining my radial direction, right? So if I draw a line from my origin to the ball, that's always going to be perfectly aligned with this arm that pivots around theta. So this seems to be my u hat r direction. And then based on the way that theta is drawn, theta will increase as the arm is pushed up and to the right. So it looks like this is my u hat theta direction. And we're also given things in this problem like r, theta dot, and theta. These are all variables that are part of the radial and transverse coordinate system. And r and theta dot, they don't show up in my normal and tangential system. So that's why it's a good guess here to say that I'm probably most conveniently going to answer this problem using the r theta system. So that means that the first thing I'll do is write down velocity in my r theta coordinate system. And again, this would be given to you in an equation sheet. Once I write that down, I know what variables I need to go find. So we need the following. I need to find r dot, r, and theta dot. So let's talk about each one of these things. R dot is going to be a little bit tricky because we are given r as a function of theta, not r as a function of time. So how do we find dr dt, question mark? Heads up, it's going to be the chain rule, like we talked about earlier. Now, r is given to us as 1.5 theta, and we need to know r when t equals to 1 second. So then my question is, how do we find theta when t equals 1 second? We need to find out what theta is at 1 second in order to know what r is at 1 second. Theta dot here is probably the easiest one to deal with because we can just take it from the problem. Theta dot is equal to 4t, so theta dot at t equals 1 second is just 4 radians. Okay, so now let's look even closer at each of these quantities. So first I'm going to say let's try to hunt down r dot. So we're going to have to do our chain rule. We need dr dt, but we're given r as a function of theta. So this is equal to dr d theta times d theta dt. So what is the derivative of r with respect to theta? Well, r is 1.5 theta, so the derivative is just 1.5. And d theta dt is 4t. And we really care about what happens when t is 1 second. So r dot of t equals to 1 second. We'll just plug in 1 second for time here, and we should end up with 6 feet per second. Alrighty. Now let's try to find r. I'm just going to use this extra space here. Let's say find r. So since r is given in terms of theta, we need to find theta in terms of t, so that we can plug in t equals to 1 second and find out what theta is. But we're not given theta as a function of t. All that we're given is the time derivative of theta, so theta dot. So if we have theta dot, and we want to find theta, I'm thinking we need to take an integral. So let's write down d theta dt is equal to 4t. I'm going to separate variables, so I'll have d theta is equal to 4t dt. I've got a d something on either side, so that means I need to integrate both sides. And now let's try to figure out what bounds we want to go from. Now this is why we were given these initial conditions up here in the problem. We're told that when t equals 0, theta is equal to pi over 3. So that gives us our initial condition. And then I really want just a generic form of theta as a function of time. So I'm just going to say we're going to go from t to any theta in time. And I can evaluate this integral now. So I should get theta evaluated from pi over 3 to theta equals 4t squared over 2 evaluated from 0 to t, which should give me theta minus pi over 3 equals 2t squared, which means that theta as a function of time is 2t squared plus pi over 3. And now if I want theta for t equals to 1 second, this is just 2 plus pi over 3, which should be 3.047 radians. So now we know what theta is when t equals 1, so we can plug that in to our r expression to find out what is r when t equals to 1. So r when t equals 1 equals 1.5 times theta equals 1.5 times 3.047 radians, and r of t equals to 1 should be 4.57 feet. Okay, and we had already found theta dot, so now we just need to plug and chug into my original velocity expression. So velocity is equal to r dot u hat r. R dot is 6 plus r theta dot u hat theta. So r is 4.57. Theta dot is 4. So u hat theta, and this will be in feet per second. And this reduces down to 6 u hat r plus 18.28 u hat theta feet per second. Okay, now we need to do something very, very similar for acceleration. So acceleration, I'm going to write my general form, r theta double dot plus 2r dot theta dot u hat theta plus r double dot minus r theta dot squared u hat r. Well, we already know r, that's 4.57. Theta double dot, what do we know about theta double dot? Well, we have theta dot. If I take one more time derivative of that, I should just get 4, always. So that's 4. R dot, we found up here, is 6 feet per second. Theta dot is given to us in the problem. Plug in t equals to 1, we should get 4. And our double dot is going to be equal to the time derivative of our expression for, let's see, r dot. What did we find for r dot? We said r dt is equal to 1.5 times 4t. So d dt of 1.5 times 4t. If I take a time derivative of that, I should just get 1.5 times 4, which gives us 6 feet per second squared. Okay, so now I just plug and chug. Plug all these values into that long acceleration expression. I should get acceleration is equal to minus 67.12 u hat r plus 66.28 u hat theta feet per second squared. And that, my friends, is example 2. So with these problems, I'm hoping you're noticing a pattern. There's kind of a pattern to the way that I did both of these problems. So I started out giving you an explanation for why it was smart of us to choose the r theta coordinate system. Okay, and usually it's because we're given variables, or we're given in the problem information about the variables that are pertinent specifically to that coordinate system, like r's, theta dots, and so forth. Now for normal and tangential, if we were given like the time rate of change of speed, that would be v dot. That's something that shows up in the normal and tangential coordinate system. So that would make me start thinking, maybe the nt coordinates are better. Then we wrote down the general form for whatever we're being asked for, whether it's position, velocity, or acceleration, in terms of the coordinate system that you chose. And again, these are given in your equation sheets, so it's really just choosing your coordinate system, and then going to find the correct expression for r, v, or a on your equation sheet. But then once you have that written down, you know that you need to go hunt down each of those terms in order to fill out those expressions for position, velocity, acceleration. So that's where I wrote down, what do we need to find? Well, for acceleration, I needed to find r, theta double dot, r dot, theta dot, and r double dot. And then I could focus my attention on each of those variables individually, which helped me kind of stay focused on one small part of the problem at a time. And then once I had all of my variables, I could just plug them into the overall expression. So that's the main gist of our theta coordinates. It would be a really good idea for you to, at this point, review and maybe compare and contrast between the Cartesian, the NT, and the R theta coordinates. These are the only three, coordinate systems that we're going to work with in this class. And you'll notice that we also only covered them up to 2 dimensions. If you go through the book, you'll notice that there are extensions of these coordinate system definitions to the 3rd dimension. Okay, so for instance, the Cartesian coordinate system would become the XYZ. The normal and tangential would become the NTB coordinate system, and so on. But in this class together, we're only going to go up to 2D. So R theta, NT. We might do a little bit of 3D in the Cartesian coordinate system, but just hold on to that thought for right now. Mostly only doing 2 dimensions. Okay, hope this helps. Thank you so much.